Now that we know all about MLE estimates, or maximum likelihood estimates, we're ready for map estimates. Maximum a posteriori. A posteriori. Some good Latin there. And map estimates are very similar to MLEs. They are also point estimates of some parameter theta. So I'm going to follow a similar way of presenting the map as for the MLE. So the setup for computing a map is the following. We're given some data, D, which is some points x1 to xn, and these are just points in some, typically in some d-dimensional real space, or more generally they could just be some vectors or scalar quantities. So we're given some data, and we assume a probabilistic model. We assume, in particular, a joint distribution on both the data and theta. And theta is going to be a parameter governing the distribution on the data. So we assume this joint distribution. So here, theta is a random variable. And so just a note here, theta, this is a sidebar, often we use capital letters to denote a random variable and lowercase to denote the value it may take. But for thetas, unfortunately, we already use capital theta for, it's standard practice to use capital theta for the space that theta takes values in, so we'll just use theta lowercase for both the random variable and its values. So we assume this joint distribution, and our goal in finding a map estimate is to choose some value of theta. So we want to choose a good, in some sense, value of theta for D. So something which is good for our data. Something which we think that the data may come from. And we choose under the map. So the map says, so this is our goal, and the map says to achieve this goal, what you should do is choose the following quantity. Choose, or a quantity, theta map, that satisfies that it is a maximum over thetas of the probability of theta given the data. And this is the posterior distribution on theta given the data. So for comparison, the MLE was the argmax over theta, or an MLE, I should say, because I'm saying A instead of the, because there might not necessarily be a unique value theta map that satisfies this. This posterior distribution, it could have multiple peaks that have the same value, or even 3 or more, or something like that, as opposed to just a single unique maximizer. And so recall that an MLE, a maximum likelihood estimate, maximize the probability of the data given theta. So this was the likelihood function, the maximum likelihood estimate, maximize the likelihood function, and this is the posterior distribution on theta given the data. So the maximum a posteriori estimate maximizes the posterior distribution. That is the map, or a map. I keep saying the map. Oftentimes it turns out that there is a unique one, so usually it's correct to say the map. Okay, so that's the definition. And I'd like to mention a few pros and cons in keeping with our tradition started in the MLE. In our discussion of the MLE, some advantages of a map estimate. One is that it's also, as with the MLE, it's usually pretty easy to compute and interpretable. So usually the computation is not too much harder than the MLE, and often it has a very natural interpretation as interpolating between the MLE and a prior value determined by this. So this thing right here, right? Maybe I should give a little more terminology. We can write this joint distribution, we can factor it as a conditional distribution on the data given theta times the marginal distribution on theta. And so I'm using our shorthand here. I'm dropping subscripts to denote that this p really denotes the marginal distribution on theta, and this is the conditional distribution. And this quantity here, this p of theta, this is referred to as the prior on theta. This is the prior distribution on thetas. So the interpretation oftentimes for a map is that it interpolates between the MLE and the prior. So another way one way you could define a joint distribution here would be to assume a prior and then assume a conditional distribution. Oftentimes that's the way many models are actually defined. Okay, so that's one pro. Another advantage of map estimates is that they avoid overfitting. So this is in contrast to MLEs. MLEs oftentimes will overfit the data, but maps, you can use maps to avoid overfitting. And this has a very close connection with what's called regularization, or in other contexts, shrinkage. I won't go into the details of what these are, but they're very, very closely related to putting a prior on theta and using a map estimate. And one third advantage, or one third sort of nice thing, is that the map tends to look like, I'll say it this way, it tends to look like the MLE asymptotically. Now remember that the MLE had some nice asymptotic properties which I didn't really describe in detail, and unfortunately the map, it doesn't have all the same nice asymptotic properties as the MLE. However, it typically will, oftentimes it will converge to the same value as the MLE asymptotically, and so that's why I put it this way. It tends to look like the MLE asymptotically, and so since the MLE has some very nice interpretations, and then it's sort of reassuring to know that the map, that your prior, when you assume a prior here, then you're sort of changing things from that natural interpretation, and it's nice to know that as your data, and this is asymptotically as n goes to infinity, where n is the number of data points. It's nice to know that as the data goes to infinity, that your prior is sort of being overwhelmed by the data. So that's a nice thing. But it's not like better than the MLE in that respect, because this is just relative to the MLE. Okay, so those are some pros, some cons of map estimates, some disadvantages. Just like the MLE, it's also a point estimate, and it comes with all the same sort of disadvantages, which is, in particular, you have no representation of your uncertainty in the value theta. If you were using, the ideal thing would be to just take the whole posteriori distribution and use that to represent your uncertainty. And it's sort of a extreme example of this is maybe a sort of degenerate example would be if your posterior distribution looks something like this. So this is the posterior on theta given d. And the map then would be this maximum, this would maximize it. And a similar sort of degenerate thing can happen for MLEs. The map would maximize this posterior, but this is just like this really little, like small spike and represents a very small part of the probability mass, whereas most of the mass is over here. So really this would be a more representative value for this distribution, but the map ends up being over here. So you have no representation of your uncertainty. And another thing I'd like to mention is that in contrast with the MLE, I didn't really go into this, or I didn't discuss it at all for the MLE, but the map is not invariant under reparameterization. The MLE has a nice property that if tau is some function of theta, then the MLE for tau, so this is a reparameterized, transformed version of theta, then the MLE for tau is just the function of the MLE for theta. So this is a nice thing that MLEs satisfy, but this is not it's not true for maps. So this is sort of a disadvantage of maps over MLEs. And one last thing I'd like to mention is that whenever you assume a prior, you assume a prior. You're making some assumptions. And although, of course, in an MLE, you're also assuming this conditional distribution on the data given theta. You're assuming this likelihood function. For when you're using a map, you're assuming even more. You're also assuming a prior distribution on theta. So a con is we must assume a prior on theta. And so a lot of times people don't like methods where you have to assume priors because you may not have a good reason for choosing a particular prior, one prior over another. So that's map estimates, some advantages and disadvantages, and that's the definition.